So let's start. Just before we start, a quick note about the core servers. There were technical issues dealt with by the IT people, and starting from yesterday, they're working. So I will send an email about that. But you should be able to use them from today. Yes. Right now we didn't change it, but we will probably give a delay because of the servers. But only the last part actually needs the server, so you can do most of the work anyway.
Are we already started for the server? Like whoever was
Yeah,
the
should work from now. Yeah. But there's a small difference in the instructions that I would need to publish the difference. All right, so let's start with the tutorial. Today we're talking about transfer learning and domain adaptation. We'll talk about what transfer learning is. We'll show two examples. One how to use pre-trained models and leverage training that other people did on large data sets for your own tasks. And another example of doing domain adaptation in an unsupervised setting. We'll implement an idea from a really nice paper, kind of see how it works together. Okay. So let's start. So let's talk about transfer learning. So far we've seen supervised learning. We had this nice setting where we had a training and test set. Usually we created them by splitting our data. And we assume that the data comes from this joint distribution of samples and labels. And we're trying to learn this posterior here. And we assume everything comes from the same distribution. And at least when we were taking our own data and splitting it, it made sense. And we hoped for generalization by taking a hidden test set. But what happens when it's not the case? When actually we can't know about anything. We don't know anything about the distribution in that we will see during test time, or we know something but we don't have labels, so we can't train on it. So in the real world, this is a major problem, and it happens almost in any kind of situation that you do deep learning. So this assumption can be, for example, invalid if you take the case of MNIST. Let's say you train on images like that, but during inference, you sometimes see images like this. So this is a different data distribution. If you think about the distribution of images of 28 by 28 grayscale images like that are from a different distribution. So your model may fail to generalize to them. And if you look at this type of images, so again, the idea is to identify digits, but it's a completely different space of samples, because we're dealing with color images now. And even the label space is different because we have 2 digits. So what if you want to use knowledge that we gained by training on this kind of distribution and somehow leverage that knowledge to other kinds of distributions? So let's be more specific about what we mean by domains and tasks and targets and all those words. So just building from the basics, we have a feature space X with this type of X. So in our examples, for example, it could be a space of color images. So if you have the space of all possible color images, 32 by 32, obviously you can imagine you have a very large space. And from that space, we take a subset, and we call it our training set. So let's say our training set is CFAR10. So we have some images from that huge space. And obviously, the distribution in our training set is not actually the distribution in the original space. We don't care about that. We care about this probability distribution P of X, the evidence distribution of our training set. Okay, so this is what we have. And we have, of course, a label space. So the labels can come from the space Y, or, for example, in binary classification 0, 1. And we may have a label for each of the samples. Okay, and as you know, in the supervised context, we want to learn this target function, which models this probability condition, this posterior condition on the evidence, on the sample X. Okay. So to to summarize what we mean by domain, so a domain will be defined by this set of the space of possible samples, where the samples are coming from, and the actual distribution of our training set. And our task will be defined by the labels that we want to predict, the space of labels, and the actual function that we're trying to learn. So this is our domain and task definitions. And so there are different settings that are possible when we talk about transfer learning using those definitions. So if we assume a source domain and source task, so let's say source domain images from MNIST, and source task would be classifying them into digits. Okay, so target domain could be one of the other types of digit images that we showed. So transfer learning deals with the case when you want to learn some target function in the target domain for the target task here. Okay, so you might have the case where the domains are different or the tasks are different, but you want to somehow leverage the knowledge from your source domain and task. So you solved, let's say, the source task, and you want to use that knowledge to solve the target task, basically. And sometimes there are other constraints, as we will see in our second example. For example, there might not be labels available for the target domain. Okay. So let's see quickly some examples. So if we have the same domain but different tasks. So this is one context for transfer learning. So again, this is our definition of a task. So again, there are two cases. Either this would be different between source and target, or this would be different between source and target. So, or both. So one example, easily you can understand, like the first obvious example, if the label spaces are different, let's say we solved CFAR 10, but now we want to somehow use our model for CFAR 10 to solve the much harder problem of CFAR 100, which has much more classes, but somehow we want to kind of transfer the knowledge or use it. So we have much more labels now. But the space of images is the same. Maybe the distribution isn't. So another case, maybe the target conditional distributions are not similar, or not the same between the tasks. Okay. So when can this happen, for example? Any ideas? Scale. Well, the example here is even if you see the exact same type of image, you might classify it a bit differently. So it might be because you believe something different about this prior for your label. In the case, for example, that the label class balance is completely different in the target. So that might be a case that happens. You train on some balance of labels, but you test on a completely different balance. Okay, and so the second type, what if we have the same task but from a different domain, the data from a different domain? So again, we can either change the space of data or the probability that we assume. So if you have different spaces, you can imagine an example of training with grayscale images, but then you care about actually color images for inference. Or let's say you have documents in different languages, so basically the words are different. So that's a simple example. And similarly, you might have different data or evidence distributions between source and target, even though the space of possible samples is the same. Okay, so easy to imagine. The space of images is your domain, but you can maybe train on hand-drawn images, but you want to predict something about photographs. So completely different distribution of pixels. Or in the document example, you're looking at the same language. It's English, but you're training on documents about one topic and testing about another topic. So the distribution of words would be different, even though the same words are there. Okay, so that's some examples. And one of the most common scenarios is this last one, where we actually care about the distribution of the data samples. So this is a very, very common scenario. Usually people refer to it as domain adaptation. So for example, with images, you train on these images of driving during the day, but what you actually care about is inference at all situations, low light, high light, night, different lighting situations. So these different types of images have completely different distributions in terms of the actual content of the data. Okay, so that's kind of an example. And basically there are lots of these sub cases, but today in the tutorial we'll see examples for mainly domain adaptation. You can see kind of going back where it assumes different domains with a single task. And we'll also see an example where we have labeled data only for the source domain. Okay. So this is kind of the scope that we're in. So let's see the first example that we'll look at in this tutorial, unless there are questions so far. Okay, so far just definitions. Let's see first kind of real world example. So this is an example that is very popular. Lots of people do this. Okay, so let's say we have a trained model. So someone trained it for us. Someone solved ImageNet, trained on 1 million images. And we have a different task, but we will somehow want to use this pre-trained model. Okay. So maybe in our task we have a very scarce data. So we can't train a very deep network from scratch by ourselves. We want to somehow use something else that someone already trained, but it's trained on a different task. So here's a common example. Let's pre-train on ImageNet with over 1 million images, and usually you train it on with very, very deep networks. Have 1,000 different classes in this data set. But what you care about is your medical images. Let's say you have medical images with only a few classes, but your data is very rare. It's hard to get labeled data in this domain. So you somehow want to use this network that someone already trained, keep some of the trained parameters or trained weights here. Okay, you want to keep them, and you want to only learn maybe part of the network, and then use it to do something else. So your task is different. You want to classify medical images, for example. So you want to leverage this pre-trained network. That's the idea. No. Yes, it's not always the last part. It's usually you can also, I'll show it. You can somehow fine-tune the rest, tune it a bit. You can learn learn a lot here, but learn less here. You can do kind of tricks like that, and I'll show an example. Okay, so generally, why would this work? At least in the case of images, the intuition should be kind of known to you already by now. So any idea, kind of intuitively, what's the point here? Okay, but why would feature extraction work when I had this kind of images, and then I care about classifying this kind of images, which are completely different? Yes, exactly, because of the interesting phenomenon in convolutional nets that the deeper you go, the more high-level features that you learn. So this is a very nice visualization. I wrote where it's from below, where what you're looking at is images that are generated by optimizing the input, kind of backpropping not to the weights but to the input of a network, and showing images that maximally activate layers of a very deep network that's trained on ImageNet. So you can see kind of what kind of images a specific layer in the deep network likes to see. So if you're in the beginning of the network, you see kind of lines and simple patterns, and then more complex patterns. And this is one idea to see what these convolutions are running. So the idea is that maybe in the first layers of a network, we have something that's common, that's needed for any kind of image classification task, and maybe in the final layers, it's more specific, like you can see eyes here or flowers here. So that's specific to ImageNet. Maybe we want to kind of change those weights in the last parts. Yes?
Go again to the previous slide. With the architecture, this one. Can you explain again what we want to do here? Like we want only to relearn the weights of the last few layers, or what?
Yeah, we want to basically, this is a fully connected layer, so we want to replace it and learn this whole thing from scratch.
Oh, only the fully connected.
But we want to somehow use this. Maybe keep it as is, maybe change it slightly. So some parts we want to learn from scratch, and some parts we want to maybe slightly modify or even keep as is, depending on what our task is.
So it is in general you want to some part to relearn and some part to.
Yeah, so this
So
is one.
It doesn't mean that the CNN stays it is and the fully connected changes.
No, it doesn't mean that. Yeah.
Is this part still supervised?
Yeah.
You said sometimes there are no labels.
Yeah, well, I'll show an example, but right now I'm assuming I have labels for my domain. In this example. In the next example, I will not assume that. Okay. So that's the kind of intuition why people do this with, especially with CNNs. Again, a very, very common thing to do. So many times people start with this idea and then kind of also over time change the architecture. But this is a good starting point for starting with a new task. Okay, so this is basically what I just said.
But what's the motivation to save time?
Yeah, because training on ImageNet takes many hours with many GPUs, and especially if you want to read state-of-the-art results. Okay, so basically, like I said, the idea is keep some parameters in base layers and fine-tune maybe some of the parameters in the deeper layers, maybe change them slightly, and completely change the classifier head, the fully connected parts at the end. Okay, so we'll show this example exactly. We'll take a deep CNN, or semi-deep, trained on ImageNet. We'll take a ResNet 18, just to make the download faster, or the size smaller that I'm downloading, because you can use a pre-trained model. You're basically just downloading the whole set of parameters for the model that someone else trained. So let's load, using Torch Vision models, a pre-trained ResNet 18. So I'm getting this model someone else implemented and trained it, and it comes with all the parameters already built in and ready to go. You can see the structure here of this ResNet. I have some input convolution. Then we have these sequential blocks called layer, but actually this is a ResNet block like we saw in the tutorial. So it has two ResNet blocks, one block here with two convolutions and then another block with two convolutions, exactly like we saw in the previous tutorials. So you have in each thing here called layer, you have 4 convolutions, and this ResNet 18 has 4 layers. And after all those convolutions, it goes into a fully connected layer that outputs 1,000 numbers, which is the number of classes in ImageNet. So this is a model for ImageNet. If I try to use it for something else, it won't work. Okay. So yeah, we can see the structure, we can see the 1,000 output classes. So first thing we want to do, let's freeze all the layers. We want to not be able to train everything. So one simple way to do that, go over all the parameter tensors. Just say they do not require grad anymore. If they don't require grad anymore, and you try to optimize, gradients will be calculated for those parameters. You can't optimize them. So let's freeze them. Now let's say we want to only look at layer 4. So layer 4 is the last 2 ResNet blocks that like we saw. Let's say we want to fine-tune only them. So we can decide to thaw them, let's say by setting their parameter required grads to true. But a different approach, and possibly in some ways better approach to do it, is that you can specify for your optimizer different sets of parameters, and for each set of parameters you can give different parameters for the optimizer. So for example, in layer 1, 2, and 3, I'm setting the learning rate to 0. So if I just do that, then even if I didn't say require grad false, I'm effectively not training. My learning rate will be 0 on those parameters. So this optimizer will know when you see those parameters from that layer, use these learning rates. And you can combine them. Basically, why would it be a good idea to say require grad true, false anyway? Exactly. It will save memory and save time. You won't have to compute gradients that you don't care about. But for example, maybe you want to fine-tune this layer and train this layer from scratch. So you might put a very small learning rate for the final layers while you actually train with a higher learning rate. Okay, so it might allow you some flexibility. So this is an approach for kind of fine-tuning. Next thing we have to do, we have to replace the last part of the network, the fully connected part. So I'm taking my ResNet as is. I'm just asking the fully connected layer at the end how many input features it has. And let's say my in my medical application, I have 13 classes, not 1,000. I care about 13, which I want to predict. So this is my number of classes, and I just set this FC module here in the ResNet to some other PyTorch module. So here I just built a PyTorch module using a sequential. So I have my sequential using two fully connected layers from the number of features originally in this ResNet. Okay, so this depends on the architecture of the ResNet. So I'm taking that number, converting it into 100 just because, and then finally from 100 features, I'm calculating the actual number of classes that I want. Okay, so now after I do that, you can see the number of original features in the input to the original fully connected layer. So now my new ResNet looks like this. You can see all those layers that were also originally there, but now the last part, the FC part, is a sequential, not just a linear layer, and it's a sequential ending with a fully connected layer that outputs only 13 numbers, which is what I want in my fake application. Okay. Oh, sorry. Or just what? Yeah, from the classification part, yes. Sorry, I kind of ruined my ResNet. Okay, so now we trained on ImageNet. Now we'll use CFAR10 as an example to show now our target domain is this CFAR10, even though we trained on ImageNet. So two important nuances. This network was trained on images, and the feature normalization that was performed was for ImageNet. So they did some normalization to the images. You have to do the same thing. You have to scale your data the same way so that the network, at least in the frozen layers, will work with it better. So that's what this transform here is doing. After that, I just load my CFAR10 data, as you would expect. ImageNet is a very large data set with 1 million images and 1,000 classes. CFAR10 has, I think, 60,000 images. CFAR10, yeah, 10 classes. And CFAR100 has 100 classes. I don't remember how many images. But it's much, much smaller. And the images are smaller. With ImageNet, you have 224 by 224. So it's larger images. And CFAR10 is 32 by 32. So it's a much easier problem. Yeah. I added a transformation here for resizing, and normalization to the same, using the same learned parameters from ImageNet. Yeah, okay. So let's see that now our model works with an image from CFAR10. So it should work. It should work and give you 13 output numbers, or raw scores, basically. And this shows that, for example, this CFAR10 image was resized to a size that the network can work with, and that we connected our fully connected layer at the end properly. Otherwise, we'd get some dimension mismatch or something like that. So forward pass works. Next thing, just set up the optimizer. So small nuance number 2 here. When you pass your parameters to the optimizer, don't pass parameters with require grad false, because they won't have a grad. The grad will be none. Okay, so that's just a small nuance. If I set some of them to false, I will just skip them using this filter here when I'm going over the parameters, and then giving only the non-frozen parameters to my optimizer. I will still save time. I still will not calculate gradients and waste time on those parameters. But this allows me to, some parameters I'm fine-tuning, some I'm freezing completely, and some at the end I'm training as usual. Okay. Another thing I did here, I added a scheduler for the learning rate. So this is also something that's popular to do when you want to use pre-trained models or fine-tune. Sometimes you want to change the learning rate during training. Maybe you want to decay it. Maybe you want it to go down and then go up. There's various types of regimes for how you should modify your learning rate. This is an example of using a built-in scheduler in PyTorch that's called reduce LR on plateau. Basically, if you give it some metric to measure, let's say test loss, if it sees that test loss doesn't change for 5 different calls, let's say, so if you call the scheduler each epoch, then if it doesn't change after 5 epochs, then the scheduler will reduce the learning rate by a factor of 0.05. So you can do various interesting things with these schedulers.
Do you want to increase the learning rate? Because if we're on a saddle point, we want to get
No, if you, let's say you're somewhere inside the loss surface, okay, if you start increasing now, you might jump out of the
but
good
now
region.
you're not on a saddle point, you want to get out of the style.
Well, you hope that if you start decreasing well into the training, you're probably in a good region now, and now you should actually decrease it so you can fine tune and find the even smaller optimum, even lower loss, basically. But again, it's completely empirical. It might not be true for you. Okay, finally, let's train as usual. So this is where you can implement your own training code. So this is just an example. I'm not really going to train it here, but the idea was to show how to use a pre-trained model, how to change the last part, how to freeze and fine-tune weights. Yeah.
Typical training time for such a process is short or longer?
Well, it will be much shorter since you're training much less parameters. If let's say we didn't use ResNet 18, we used ResNet 152, which is 152 convolutional layers, or something like that. So most of them you keep completely frozen. Or if you don't, then you train them with very small learning rates.
But then you still have to calculate credit.
Yes, but
So the difference is not.
but you might see results much faster than you if you start from scratch training that huge network. It might start working for you because the only thing that's really changing fast is your last fully connected part, and it's already using information from highly trained convolutional filters. So it has a good signal to work with, even from the beginning. So you should see good results much faster if you do this technique.
But it kind of depends on the task.
Yes, of course. If just because it's an image, yeah, I mean, let's say I'm trying to classify images that are completely different. I don't know, they have
And
completely
if you choose
the pre-trained
a
model.
good pre-trained model.
Of course, you have to decide what your baseline is. Of course, everything. This is just a very basic example, to kind of a common scenario where you have a different type of image. Okay, so that was the first part, example number 1. So now the second example is unsupervised domain adaptation. So now it's unsupervised because we will not have labels in the target domain. Okay, so this is the example now. Our source domain will be MNIST, again. And our target domain will be a kind of modified version of MNIST, where someone generated these images from MNIST. It's called MNIST M. So they segmented out the number and gave and put some background with some changing textures. And now the numbers are a different color, and you have different kind of crazy backgrounds for each number. Okay, but the actual task is the same, to classify the digit, but the input distribution of the data is completely different. And as I said, we do not have the labels on this target domain, only on the source domain. So we want to train a classifier on the source domain, but so that it will work on these images, actually. So first,
Now you don't really want to change the architecture of the fully connected, right? Only to relearn the weight.
this is a completely different example, so I'm not going to do any pre-trained network here. Okay, so again, we assume no available levels. So first of all, why do you think it would not generalize? I mean, why won't it work if let's say I take my CNN that completely solves MNIST, works great. Why would it not generalize to MNIST M? Any ideas?
Because the normalization you made is different.
Well, nothing really constrained the convolutions to look kind of intuitively. When you look at that, you're concerned about the shapes, right? But nothing constrained the optimization of the convolutional filters to only look at the shapes. They might be very, very dependent on the specific distribution of context and colors. So we kind of intuitively, we need a way to force our CNNs and our learned filters to kind of only learn features of the shapes, not the color distributions, in this specific task at least. In this specific task, we want to kind of force these CNN features to do something a bit different that will still allow them to classify, to learn features that will enable classification in the final part, but will not depend on any kind of color-related features. So we will use an approach from a nice paper that's called domain adversarial training. And the approach is like this. So the top part here is just a general deep CNN. So we have this CNN part here, the feature extractor. So we extract convolutional features from our input image. After we have these convolutional features, we have this fully connected part at the end as usual. So this part is trying to predict a label. Okay, so we have something that predicts class labels. Let's say a few fully connected in a softmax, and we get some prediction. But the nice part here is the second part here. So it's like we have two different heads. We have one normal head to classify what digit it is, and another head that's purpose is to classify the domain. It says whether the image comes from MNIST or comes from MNIST M. So we have other fully connected layers here that look at the same features, and their job is to say whether this feature vector comes from MNIST or comes from MNIST M. Okay, so you're trying to train that, and you do a nice trick here. You add something called the gradient reversal layer, where basically when you calculate this loss, you propagate it backwards, and when it reaches here, you flip the gradient. You give it a negative factor to the gradient coming from the domain classifier. Okay, so the idea here is to kind of ruin the ability of these CNNs to extract features that allow classification of the domain. Okay, so that's why it's kind of adversarial. So you're trying to classify the domain, but when you reach here, you're kind of using a negative gradient. So you're trying to kind of fool the CNNs into not being able to classify the actual domain. Slightly similar to GANs.
What's the point of this? Why don't we want to know the domain?
Because the idea was that you have bad generalization. You can't generalize from MNIST to MNIST M because nothing told these convolutional features here to only look at the shape. Now, if you create this domain confusion, you force them to be able to classify digits, but not be able to classify domains. Basically, you're forcing these convolutional filters to do something else. They have to find a way to work for the classification task here, but not for that one.
So you have different parts of the same network, just and you have like again just a more complex loss function or something.
I will show the implementation. It's simpler than a GAN. It's much simpler. You will implement a GAN, by the way, in the next homework. So, yeah. The labels exist, but we're not going to use them. We don't have them. Let's say. Okay.
So how do you know that you classify them?
So when you input an MNIST image, you pass the image through here and through here. And when you take a MNIST M image, you only go to this path and calculate the loss from here backwards. So for MNIST M, you don't have the top path. That's it.
And you train on a mixed data.
You train from both of them, yeah. I'll show the training.
And this label is binary, it's 1 bit, right?
Yeah.
And it will be, you will get a loss only if it will be labeled as MNIST, right?
Well, it's you can think about if it's, let's say 0 is MNIST and 1 is MNIST M, but you know the original domain. For each image, you know the original domain. It's like a label that you have. You just don't know what digit it is. if it's from MNIST M, you don't know what digit it is. You don't have that label, but you know what domain it is. So you can train this. You can train this classifier with the domain. Yeah.
Is this more efficient than simply to train with those sets?
This is different. The previous example is not possible here since we don't have labels in the target domain. So I can't train it like before. So this is a different case. It's harder case. Okay, so what I said now is basically what's written here. So I'm not going to go over it again. That was the general idea of the paper. Now let's kind of see it in action. So first, let's just load the data. So I have this. I'm not showing it, but I have this dataset class that loads this MNIST M data. You can look at it later if you want. It's like you already know, a PyTorch dataset object. Nothing really interesting there. For some reason, it's taking a long time to load it. Okay, so I'm just showing three images from MNIST and 3 images from my loaded MNIST M. So you can see, as I promised, we have the same digits but with different kinds of weird backgrounds, and even inside the digit, it might not be the same color. So it's a much harder task. So that's our data. Let's look at the model. Okay, so the model directly from the paper is a simple CNN part. Okay, so we have 2 convolutional layers with pooling and stride. And this is the fully connected layers that classify the digit. And we have this gradient reversal layer. Okay, and then we have this fully connected part for classifying the actual domain. So they wrote here 1 unit in logistic, and here 10 units in softmax, but we will implement it with 2 units in softmax. It's the same thing. Just to keep it consistent. Okay, so the first question though is what is this gradient reversal layer doing? And how can it work? I mean, how does it work? What's it doing? Okay, so think about it for a second. You have something that during the forward pass, it should not do anything, basically, right? You don't want it to do anything. You want to take these features here as is, but during the backward pass, you want to multiply the incoming gradient, okay, by a negative factor. So it's not a real function. So you can't have a function that does nothing, but its gradient is a negative factor. So it's not a real function, okay, but we can still implement it by kind of hacking into the forward-backward functionality of PyTorch. It's not really hacking; it's just using a different type of API. So we'll use an object called autograd function. This is what PyTorch is using to do operations on tensors. All the operators on tensors. These are where you can actually define your custom backward if you need a custom backward. So let's have this gradient reversal function. It's a function, like I said, from autograd. In the forward pass, it takes our input x and alpha, which is it was lambda in the previously, but this is the factor. We just save it, okay, and we return x. There's no op, not doing anything. In the backward pass, we're taking our grad output. So remember, like in the homework, you saw what your input here, right, is the derivative of the loss with respect to what you output here, right? So this would be dl to dx. You're taking that and you're multiplying it by negative alpha, negative what you save, like the constant, and then returning that. So you're flipping the gradient and factoring it by alpha.
Sorry, where's the gradient output for?
This is what's coming in to the backward pass from the end. This is the upstream, let's say, loss. You're taking the final loss number,
Right.
and you're backpropping its gradient, and you're calculating along the way, right, the gradient of the loss with respect to all the parameters along the way. So what your input here to this backward will be the derivative of the loss with respect to what you output from your forward. It's exactly like in the homework where you implemented your blocks.
Yeah, but it's only halfway that you.
You're somewhere in the middle now, yeah.
This starts, the backward starts from the middle backward pass, from mid backward.
Yeah, this is a function specifying what this specific layer, let's say, is doing.
Okay.
How to do the backward for that. It's not the backward for the whole thing. It's exactly like in your homework assignment.
How do we determine what's the alpha?
I'll show it after. Here it's just an input. I'll show it. Okay, so let's see what this is doing. Let's say we have a tensor W with required grad equals true. I'm doing some linear operation, 2W plus 1, and then passing it through my gradient reversal layer. Okay, so as you can see, it did the 2W plus 1. This had no effect in the forward pass, but look at the grad function now. It's called gradient reversal Fn backward. So something is going on here. It has a custom backward function. Now let's say my loss is just summing these numbers, and I'm doing backward from this loss. So this is where my custom backward code will be called at some point during this backprop. Okay, and I'm getting negative numbers here. Okay, makes sense, since I multiplied by a negative factor. And if I try to just give you a visualization of the computation graph, you can see this parameter tensor went through a multiply and an addition. Then it went to this gradient reversal layer, and then it was summed. So seems to be working like we expect. Now actually, let's implement the model. Now we have this gradient reversal layer. Let's implement the model. Okay, so nothing that shouldn't be already familiar to you. So I'm going to go over it quickly. The feature extractor part. This is the convolutional part that both of the classification heads will be using. Okay, so this is the joint part of the model. So we have a convolution. We're starting with 28 by 28 MNIST images. You can calculate using the formula that I showed a few tutorials ago. The output spatial extent. After this first convolution, then a max pool will cut the spatial extent in half. So after you have these two convolutions and two max pools, you have a dimension of 5 by 5. Okay. Then we have two classifiers here. By the way, the number of features will be 50 because of the number of output channels by 5 by 5 spatial extent. So this is the number of features. So when we create a linear here, a fully connected layer, we want to convert that number of features to 100, and then keep going 100, 100, 110. Finally, we have 10 output numbers and then a softmax. Okay, and for the domain, same idea. We start from the number of convolutional features, but we go down to 2 and softmax. Okay, so basically same idea, starting from the same number of features, going down to a different number of classes. In the forward pass, okay, we're taking our input image. Here, in the case of MNIST, it's just one channel, so I'm just replicating the single grayscale channel to 3 color channels. That's what this is doing. I'm extracting the convolutional features. I'm flattening them. Okay, so this would be now batch by features, batch by number of features. Then I'm passing the features through the gradient reversal layer. I'm applying the function that I have using this lambda, which is a parameter that I get from the outside. Okay, talk about that in a second. Now I have my features and my features after the gradient reversal layer. So the features, I'm giving that to my class classifier, and the features after the gradient reversal layer, I'm giving that to my domain classifier here. So now I have a prediction for the class and the prediction for the domain. So this will be 10 numbers, and this will be 2 numbers. And then I return both of them. I return both of this prediction and that prediction. Okay, so why are we letting lambda change from outside during training? This is not the learning rate or anything. This is the factor that we give to the negative gradient. So what's the point of changing it during training? Any ideas? Decay, but why would we change it? Let's say I'm starting from a lambda of 0. Why would that make sense? Okay, So the idea is that initially you're starting from scratch, so your convolutional features are basically horrible. They're not doing anything. So you can't classify the domain anyway. So it's a better idea to initially set this to 0, let your convolutional features train a bit using the first head, okay, first fully connected layer. So your convolutional features are getting better, and then you start increasing lambda to start inserting this confusion about the domain. Okay, that's the idea. So this is a formula that they used in the paper. I just copied it as is, and it causes a nonlinear kind of movement of lambda from 0 to 1. And it's because we want to train the convolutional features before we start actually training the domain classification. All right, so let's see that this model works. So just loading images from my source and target domains. You can see the shapes. This is an MNIST image, a batch of 4 MNIST images, and a batch of 4 MNIST M images with 4 labels, but I'm not going to use these labels. You can see my class predictor returned my 10 numbers, and my domain predictor returned these 2 numbers. So makes sense. Okay, let's train. So we have these 2 losses here for each of the different tasks. Basically, it's the same. You don't really need 2 instances, but generally you can use any kind of loss you want for training these 2 different heads. And let's show the actual training code. So here, this is not the regular training loop. There are some nuances here, so let's look at this for a second. So first of all, what I need to do, I need to go over MNIST and MNIST-M, both of my datasets at the same time, kind of. So I'm not iterating over these data loaders directly. I'm creating an iterator for each data loader, and I will use these to load the data. I'm just going over until a fixed number of batches, which is the maximum number that I just set it for demonstration. And I will stop after just 10 batches just to show you. But let's look at the concept. So first of all, we will calculate this gradient reversal layer lambda by using that formula that I showed you, and it's just using p, which is some number between 0 and 1 that's showing the progress of training. So initially p is 0 and it's going to 1, and it's causing lambda to increase. So this is just a simple calculation for lambda. Now the interesting part is that we train separately on the source and on the target domain. So let's start with the source domain. So for the source domain, I'm taking the next batch of images and their labels from the source iterator. So I have MNIST images and MNIST labels. And I'm creating labels for the domain. So my domain is MNIST. Let's say I'm marking MNIST by domain 0. So I'm generating a vector of zeros, okay, with the batch size elements. So this is my labels for the domain, and these are my labels for the actual class. Now I'm feeding my model my images and this gradient reversal lambda. Like I said, I'm feeding it to the forward because I want to change it all the time. And I'm getting predictions for the class of the image and the domain of the image, or images because it's a batch. Then I'm taking my class predictions and using my class labels, okay, computing the loss for that, the label loss in the source, and computing the domain loss in the source. So I'm taking my domain prediction from the model. This is the output from the second head, and my generated domain labels, which is just zeros. Okay, I'm calculating the loss on that. I want these predictions to be 0. So now I have these 2 losses. On the target domain, I'm taking the next batch of images from MNIST-M, but I'm ignoring the labels. I'm doing unsupervised domain adaptation. I don't want labels from MNIST-M. I'm ignoring them. And what I am doing, though, is I'm creating domain labels for MNIST-M. So now I'm taking 1s instead of 0s. I'm marking this domain by 1. So I have this this vector of label 1, which will represent the domain MNIST-M. I'm feeding that to my model, okay, these target domain images, and I'm only looking at the prediction for the domain. I don't care about the prediction for the class labels here. I don't have labels anyway, so I don't care about the prediction. Just the domain. So now I have only one loss. I'm comparing my domain prediction from here to my generated domain labels from here, which is 1, the number 1. Okay? Now I have 3 losses. The source domain label, source domain domain, and target domain domain. Okay? Taking my 3 losses, just summing them. You can actually weight them if you want. And stepping backward through all 3 of these losses. So when you do that, the 2 domain losses will actually have to step through the gradient reversal layer. Okay, so this is what inserts your domain confusion. Okay, that's basically it. Just an example. I'm training for 10 batches. You can see kind of what's going on. It's starting to work. Losses are kind of going down. So that's an example. And just to end the idea, let's visualize the embeddings. So if we visualize the learned features at the end of the convolutional part using a technique for dimensionality reduction, so you can take these features and reduce them to a 2D plane with a technique called TSNE. You can see before domain adaptation, the blue dots are images from MNIST. So you had these regions in the feature space that were different, depending on the class. But from images from MNIST-N, it was obviously much harder to classify them. So this is the visualization of the feature space. And after the domain adaptation, you see a completely different image of what's happening in the feature space for the MNIST-M images from the target domain. Okay, so that's it. Thanks.